Welcome back, everybody. So, the last few lectures have been pretty tough sledding, I know, right? We have done extremely important mathematics, and of course, that means it's probably extremely difficult mathematics. This is, you know, the heart of what we're trying to get at in the first part of this course is getting to the theory behind calculus, really understanding what it means for sequences to converge, and then of course we will quickly move to talking about not just sequences but functions and how limits for functions work. And once we talk about limits of functions, then we'll suddenly be able to talk about derivatives and integrals and everything else. So this is sort of the gateway to that really understanding the theory behind calculus. Okay, so we've talked about the formal definition of what it means for a sequence to have a limit. We've done lots of examples of those. So now we can use this definition to prove a couple of theorems. So here's a couple of fairly obvious theorems. First, every convergent sequence is bounded. Now, just pause for a second. Uh, that Why do I say that's obvious? Well, if you got a sequence that goes somewhere, right? In other words, if a sequence say is converging to 7, that means eventually all the numbers are getting close to 7. Um, so what does that mean? Well, um, if the numbers are all pretty close to 7, then well, at some point they're not going to be any bigger than 8, right? And so from that point on, they'll be bounded by 8, and there couldn't have been very many at the beginning that weren't very close to 7, otherwise it wouldn't have converged. So I just take the upper bound of those finitely many few at the first. And of course, that's the way the proof's going to work. So to remind you what it means for a sequence to be bounded, again, everything revolves around definitions, right? If we don't know the definitions, then we don't know what it is that we're proving. What it means for a sequence to be bounded is that if you think of all those terms in the sequence as a set, the set would be bounded, right? What does that mean? It means an a bound, so that for every little n, the absolute value of Sn is less than or equal to this bound capital M. Right? So what we need to do is assume we're going to do a regular direct proof. We're going to assume that Sn is a sequence that converges, and then I'm going to have to prove, direct proof. I got to prove the Q part, assuming the P part. I got to prove that there exists a capital M, so that absolute value of Sn is less than or equal to M for all the n's. So that's an existence proof. So I'm going to do that constructively. I'm going to tell you what the capital M should be. So here we go. Let's assume the P part, the beginning of this implication, that Sn is a convergent series and it converges to some number S. Now, what do I know about that, right? Again, remember how we talked about how you do a direct proof? You write down what you're assuming, and then you write down what that tells you, and then we hope something strikes our imagination. Then, so what I know is the definition of convergence. I know that for every epsilon, there's a capital N, so that blah blah blah. So here's what I'm going to do. I'm going to pick an epsilon, right? Again, I could have said fix epsilon greater than 0 like we did in those last few examples, but I wanted to do something that was different, just so you would see that it doesn't could be something different. You just pick any epsilon, okay? Then according to the definition, because we're assuming that the sequence converges, right? Again, we're assuming the sequence converges. That's part of the fact we're doing a direct proof here. Um, because we know the sequence converges, as soon as you give me an epsilon, there will exist a capital N. Here's where my capital N is going to come in, right? There will exist a capital N, so that whenever little n is bigger than or equal to that capital N, that implies that the distance between Sn and S is less than epsilon. Okay? Or another way to say that is, if little n is bigger than or equal to capital N, then, well, let's play with that absolute value stuff, right? One way of saying the distance between Sn and S is less than epsilon is to say that Sn has to be smaller than S plus epsilon. I think about what that means, right? If I'm at S, remember those little green bounds we had on a few videos ago when we were first drawing pictures of what it meant for sequences to converge. Um, if I look at the neighborhood s plus epsilon and s minus epsilon, right? Those are going to be all the points that live within a distance of epsilon from s. So in other words, another way of saying that absolute value inequality is that Sen lies in a neighborhood around s of radius epsilon, and of course another way of saying that is that Sen is less than s plus epsilon, and of course bigger than s minus epsilon. But I don't really need that part because of the proof I'm trying to do. So Sn can't be any bigger than s plus epsilon, otherwise it wouldn't be within epsilon of s. Oh, awesome. Okay. I know that SN can't be very big. Again, in the example I was thinking of a second ago, imagine that SN's converging to 7. At some point, it will have to certainly be, all the terms will have to be smaller than 8. Okay? Imagining that epsilon were like 1. So from that point on, 8 is an upper bound. And that's what will happen here, right? S plus epsilon is an upper bound for the tail end of the sequence, right? All of the infinitely many terms which happen after capital N, right? All of those terms are bounded by s plus epsilon. And before that, right, I'll have S1, S2, S3, S4. I don't know what those things are doing. And I don't really care, right? Because there's capital N of them, but again, that's only finitely many. After that, which is the hard part, all those infinitely many terms lie inside that green band around S. They are all smaller than S plus epsilon. And so I just take the maximum of the S plus epsilon and whichever of those first terms may have been the biggest, and that will be my maximum for the entire sequence, right? That will be bigger than everything else in the sequence because whatever those first few terms were doing, again, there's only finitely many of them, so it makes sense to just take the maximum of finitely many things. I've got capital N of those, take the biggest one, or maybe S plus epsilon if that one turned out to be bigger, and all of my terms will be less than or equal to that capital M. So there we go. My sequence has to be bounded. Another theorem that we can get that's again kind of obvious, but the sort of thing that if we're going to prove things rigorously and really understand what's happening with calculus, we have to actually show this stuff to make sure that it is true. Because, like I said, weird things happen that you don't expect, and until you actually sit down and prove that it's true, we don't know that it's true. So if a sequence converges, the limit is unique. Okay. Another way of saying that is if a sequence converges to a number, it can't converge to a different number. That's what it means to say its limit is unique. That's fancy math speak. Um, Again, the idea is if the limit is 7, it can't also be 12, right? A sequence can't have two different limits. Um, well, yeah, duh, right? Because if my sequence is getting close to 7, it can't get close to 12 because 7 and 12 aren't close, right? So that's the way the proof's going to go. Okay, so let's do a proof by contradiction. We've been doing these direct proofs for a while now. Let's try a proof by contradiction. Let's suppose that Sn converged to S and to some other number t, presumably different. Okay, well, what do I know? I know the definition of convergence. So if I pick some epsilon bigger than 0, then there will be a capital N. Right? Well, why did I write capital N sub S? Oh my gosh, it's like a sequence. No, no, it's not a sequence. It's I need to decorate that S somehow so that I know this is the N that goes with S. Okay, so bear with me for a second. Um, if I know that Sn converges to S, the definition says that there is a capital N, so that whenever little n is bigger than or equal to the capital N, that says the distance between Sn and S is less than. Well, I wrote epsilon over 2. Why did I do that? I'll tell you why in just a second. Um, is that okay? Yeah, it's okay. And again, I'll explain that in just a second. But I want to say where this capital N and why this has an S at the bottom. It has an S at the bottom because this is the capital N that I'm going to use to show that Sn converges to S. I could play the same game and get a capital N that goes with T Because again, I'm assuming that Sn converges to t. So there'll be some kind of capital N, so that whenever little n is bigger than or equal to capital N, then the distance between Sn and t is less than epsilon. And again, I put a half there. I'll come back to that. So does everybody feel okay about the SNs? Sorry, the n sub s and the n sub t. That's not a subscript. It's not a sequence like Sn. The n sub s. Boy, that gets confusing, right? Mathematicians love to make things complicated. I'm not so much making that a subscript. I'm just decorating it somehow. So if you don't like using n sub s and n sub t, you could call this capital S if you want to, or call it capital T. Or put a hat or a funny squiggle on your N. I just need some way to tell those two letters apart. And so to keep track of which letter goes with which, I'm going to use the little subscript. But again, there's nothing magical about that. Those are just two different capital N's. One that goes with S and one that goes with T. Okay, now why in the world did this epsilon over 2 come up? How in the world did you get that? Did you get the half? Wait, come back. Well, remember what the definition of convergence said. And we'll see this idea over and over and over in what's coming. The definition said for every epsilon, okay, any number that you pick, right? For any number that you pick that's green there in our definition, there will be a capital N that works so that blah, 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 less than epsilon. Okay? That has to happen for any epsilon, right? Right? That's what the definition says. Now, of course, epsilon is just a placeholder. It's just a letter that's in there as a placeholder. So another way of saying the definition is for any green thing that you give me, there has to be a capital N so that blah, 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 less than green thing. Okay? Now, what I'm going to do, because of the way I'm going to make the proof work, I don't want to use epsilon as my green thing. I'm going to use epsilon over 2 as my green thing. Why? Because I got two different things, and by doing epsilon over 2, well, you'll see. Okay, so here's how I'm going to make this work. I'm going to pick a capital N, which is whichever one is bigger, n sub s or n sub t. Okay, I just need something that's going to work. That's whichever one's bigger. Okay, because remember, what does this say? When I get far enough out in my sequence, right, get past the n sub s term, everybody after that is within epsilon over 2 of s. When I look at the n sub t term, right, everybody after that is within epsilon over 2 of t. Okay? So I just need a capital N that's the biggest of the two, so that if I'm bigger than capital N, I'll be bigger than both n sub s and n sub t, and so I'll be within epsilon over 2 of both s and t. And of course, that's where my contradiction is going to happen, because if little n is bigger than capital N, it'll be bigger than both n sub s and n sub t, so both of them will work. Now, how far apart are s and t? Again, this is a super clever trick. Okay, I'm going to use the triangle inequality here. I'm going to take the distance between s and t, and I'm going to add and subtract s sub n in the middle of that absolute value, which looks like I made things worse, right? I have s minus t. That looked nice and simple. And now I change that to s minus s sub n plus s sub n minus t. Now, of course, I haven't changed anything because I have a minus s sub n and a plus s sub n, right? So I haven't changed anything, but I get to do something really cool. I'm going to do the triangle inequality, and remember how that works. I can break the absolute value up and take the absolute value of each piece. And I'm going to do that by breaking it there between the s sub n's. So I'll have an s minus s sub n, and I'll have t minus s sub n, although the way I've written it, I'll keep it in this order. The order doesn't matter, of course, because the absolute value, s sub n minus t. And what I know about each of those pieces, right, we recognize those now, those are the pieces that should be less than my green thing. So each one of those should be less than whatever I picked in the definition. And I picked epsilon over 2, well, exactly for this reason, because epsilon over 2 plus epsilon over 2 is epsilon. Okay, that just makes it look nice and clean, because what I now have, if you stare at this long enough, you'll recognize as an old homework problem. S minus t is now less than epsilon for every epsilon, because epsilon was arbitrary, right? So remember, we had an old homework problem that said if you have the absolute value of s minus t is less than epsilon for all epsilon, that means S must equal T. So I pull out that old homework problem, and that says S has to equal T, and there's my contradiction, right? The end of my proof, because if I started with two different limits, now I've shown that they had to actually be the same.